They have, in the 70 years that we've had them available, they have saved over 200 million lives. They have increased the lifespan of the average human being by 20 years. And for all of that, they're relatively inexpensive. And you don't need to take them for a very long time because they usually cure whatever infection they're treating in a pretty short amount of time. The problem with antibiotics is that resistance to them evolves. The bacteria that are treated with antibiotics can become resistant to them. Usually within 3 years of the clinical introduction of an antibiotic, antibiotic resistance has been detected in the clinic and is spread throughout the world, and then after that point, it just continues to increase in frequency. The way that we've always handled this is that pharmaceutical companies have always designed new antibiotics. So bacteria become resistant to one, we just kind of cast it aside and move on to the next one. This whole paradigm changed though in 2005. The pharmaceutical industry decided that it was no longer the most profitable area of drug development. And so they completely abandoned antibiotic creation. And so antibiotics that are useful are rapidly becoming extinct, and there are almost none in the pipeline for future use and future approval. To make this problem worse, those that are in the pipeline are going to be very expensive. They already are. Right now, the money that is set aside by funding agencies to address the problem of antibiotic resistance is actually being used to fund drug companies to develop new antibiotics. And when those antibiotics are developed, you know, the 4 or 5 that we have in the pipeline, pharmaceutical companies are talking about charging for them the same amount as you would charge for a course of chemotherapy. So we're talking, for antibiotics, the price is going to jump from tens to hundreds of dollars to tens of thousands to hundreds of thousands of dollars. And so this is a huge problem. And so me and my research team, we started thinking about the good old days, the 1960s. I wasn't alive in the 1960s, but they were the good old days for antibiotics. Antibiotics were very cheap, and they were very effective back then. And so we decided, what the heck, we are going to build a time machine, and we're going to travel back to the 1960s because we want to save the antibiotics that we have and make them as useful as they once were. So the antibiotics that we're most interested in saving are the beta-lactam antibiotics. This includes penicillin. I think everybody's probably heard of penicillin. The reason the beta-lactams are the most important to save is for those who are not allergic to penicillin, they are the least toxic, and they are very effective against a large range of bacteria. The 3 classes of beta-lactams we're most interested in saving are the penicillins, the cephalosporins, and the beta-lactamase inhibitors, because most beta-lactams exist in those 3 categories. Our time traveler is the 10-beta-lactamase. So the 10-beta-lactamase is this incredibly common antibiotic resistance gene. It's found in gram-negative bacteria, and it has demonstrated this enormous evolutionary potential. It started out conferring resistance to penicillins only, and that range expanded, and then it has evolved the ability to confer resistance to cephalosporins and to beta-lactamase inhibitors. So we would really like to take this incredibly common resistance gene and push it back to where it was at in the 1960s when it was first identified. The 10-beta-lactamase has evolved all these abilities by acquiring and accumulating amino acid substitutions in its protein structure. Most of the 10-beta-lactamases tend to have 4 or fewer amino acid substitutions, and there seems to be kind of this biological threshold at that level. There are a few who have gone past it, And I'm not going to get into those, but this 4 seems to be kind of the real sort of a soft limit on how many substitutions they can acquire. So we decided to take a TEM enzyme that had 4 substitutions and examine how it evolved and see if we could push it back to TEM1, which was the ancestor of the TEM. So here's TEM1. It has no amino acid substitutions in it, and it can hydrolyze penicillin. By adding 2 amino acid substitutions, N69L and N276D, the 10-beta-lactamase obtains the ability to confer resistance to beta-lactamase inhibitors. 2 other amino acid substitutions, E104K and G238S, give it the ability to confer resistance to cephalosporins. And if you combine all 4, as has happened in the TEM50 enzyme, then that enzyme can confer resistance to penicillin, cephalosporins, and beta-lactamase inhibitors. So this is a really problematic enzyme. And the one that we've chosen to focus on is an initial model. So we wanted to explore the evolution of TEM50. So the way we did this was we took all of the mutations, those 4 mutations that have been found in it, and we created in the lab mutants that contain all 4 of those mutations in every possible combination. Some of those have been found in the clinic naturally. They have a TEM name. They only get named if they're found in the real world. And then the others are just kind of artificial constructs we created in the lab. And then we gave them this binary code allele, which is not super complex, but it's used in some of the figures. And so all this really shows, the binary code, is if a substitution has occurred or not. So in TEM1, it's 0, 0, 0, 0, because there are no substitutions. In TEM50, it's 1, 1, 1, 1, because there are 4 substitutions. And so hopefully that makes sense. It's just this really easy way of going, you have a mutation here or you don't. Okay, and so then we measured the fitness effects of every one of those mutants. So on these plots along the y-axis, fitness is shown. So if the value is high, that means that TEM mutant made the bacteria very good at growing in that antibiotic. If the value is low on the y-axis, it means they hardly grew at all. And so we did this for all the mutants, and we plotted these fitness landscapes. The only thing you really need to get out of this figure is that the fitness landscapes are really different. And I think, whatever your background, you can see that. These are different. And that difference suggested to us that there are trade-offs going on in evolution. So as you evolve the ability to confer resistance to one antibiotic, you lose the ability a little bit to confer resistance to a different antibiotic. And so the next sort of logical leap from this was, well, there should be a sequence of antibiotics we can use in a particular order that can push evolution in reverse. So we have the TEM50 enzyme here in the present, and we wanted to make it evolve backwards to where TEM1 existed in the 1960s. And so you can't have a time machine without math. We brought in really the A team of mathematicians. We got Berkeley math people working on this, and they're good. I love working with them. And so what we did is we took all of my fitness measurements and we ended up transforming them a little bit and putting them into a fitness matrix. And then we did matrix multiplication, which it's okay if you don't know what matrix. Math should be mysterious, and it's okay if it is. So we multiplied all these matrices, and then at the end of it, there are so many results from this, that we had to develop a computer algorithm to search through all the results to find the best sequences of antibiotics for pushing evolution in reverse. And so we did that. Here is sort of a summary. So over on the left-hand side is sort of the diagram of doom, where you have antibiotics pushing the evolution of TEM50. So TEM1 is the 0, 0, 0, 0 there at the bottom, and TEM50 is the 1, 1, 1, 1 at the top, and all the other guys are the intermediates in between. And so every time a mutation is going to get selected for, we show which antibiotics are going to select for it with the highest probability. But over on the right-hand side of this plot is sort of the diagram of hope. These are antibiotics that actually select for reversion of the substitutions. And so by looking at this diagram on the right more closely, we can identify many pathways from TIM50 back to TIM1. We can identify the antibiotics that select for that reversion in evolution. And then we computed the probability, and for just this one pathway, there is a 62% probability of this pathway working. There are other pathways that incorporate many of the same antibiotics, and so I think that as we continue to develop the math, we'll be able to find the overall probability of these drugs working through any process, and it will be higher than 62%. And so what I have shown you is that it is possible by using antibiotics that are inexpensive and already available to us, we can reverse the evolution of antibiotic resistance and help antibiotics become useful once more. And the work that my lab is doing right now is to try to figure out at what scale we need to start cycling these antibiotics. Should it be in individual patients? Should it be in hospitals? Should it be at a community level or an agricultural level? And we still don't know the answer to that, but we are getting there. And thank you for your time and attention.